In this unit, we're going to look at how we can use our root locus to design a system. And so we kind of touched on this a little bit in the previous unit. So on pages 721 to 723 in the notes on Canvas, we looked at an example and we adjusted the system gain. And so by adjusting that system gain, we were able to get some desired transient response. And so we know for our transient response, parameters of interest are our percent overshoot, our peak time, TP, and our settling time, TS. So that's typically what we're looking for. However, in that example when we were just adjusting the gain, what we saw is that we could only specify one. So we could only specify one of those three performance characteristics. So we weren't able to, for instance, get a desired percent overshoot and a desired peak time. So we had to choose one or the other. And so what we're going to do in this unit is sort of delve into that problem a little bit deeper of how can we adjust more than one of these desired system specifications. So ultimately, the problem, which is sort of the same one we just discussed, stated in a different way, is that we're limited to points that are already on the existing root locus. So we're limited to responses that exist on the root locus. And so this is talking about the case where we're just adjusting the gain, as we saw in that previous example. So I think this is a little bit easier to consider graphically. So let's consider some simple root locus here. So again, notice I've got our open loop poles indicated with green X's, and our root locus in blue follows all of the plotting rules that we specified in the previous section. So let's say we want to have some system with a certain percent overshoot and a certain settling time. So we want to design a system with some percent overshoot, let's call it percent overshoot sub 1, and we also want to have some certain settling time, TS1. And so we're going to put a pole on our system up above here in a minute, but let's say that this corresponds to some pole we're going to label as B. Okay? And so, of course, if we are talking about a percent overshoot, like we've seen in our previous notes, that's going to correspond to a radial line. So I'm going to use pink here so this is nice and easy to see. So we've got some percent overshoot line here. So that's percent overshoot 1. And we know as well that our settling time line is going to correspond to a vertical line in our S-plane. So let's say maybe our settling time T1 is something like this. So this is TS1. Now, of course, what we're looking for then is the intersection of those 2 points, or those 2 lines rather. So a settling time TS1 and a percent overshoot percent OS1 is going to correspond to this point here. And so we would say this is pole B. And so, of course, the problem is we can see that this point B, or this pole B, is not on the root locus. So not on our root locus. Now, of course, that's a problem if we want to realize that. So if we were just doing our gain adjustment, we could do a couple things. Of course, we could choose one of the two, like with our example last time. Maybe we say, all right, let's just choose this point A, or this pole at position A, and that's going to give us our, and so let me move this a little bit, that's going to give us our percent overshoot that we have desired, but now we're going to have some different settling time line, which is going to be something like this. Try to get that a little better lined up. And so that's going to be some TS2. So if we choose this point A instead of B, again, we've met, so let's say at pole A, we have met our percent overshoot. So we have that percent overshoot 1, but we have this TS2, which is going to be greater than TS1, which is, of course, undesired. So there's really nothing else that we can do with gain adjustment. So similarly, we could choose this point down here if we wanted that settling time TS1, and actually we can't really choose that point, I'm realizing, because of course we don't have an underdamped response there. So that's going to be an underdamped response, and so maybe that response time is just going to be too long for whatever system we're talking about, so we don't even want to consider that. So let's sort of take this back to our transient response in our time domain and sort of keep in mind what this physically looks like. So let's draw a plot for our C of t over time. And we're going to draw our response for a closed loop pole at point A and point B. And so to help me sort of try to draw this a little bit more accurately, let's put a C final line in here. Okay, so that's going to be our C final. So we'll just call it C sub F. And so we're going to have sort of course, two basic curves. And I know that looks like that bottom curve's not quite lined up. Let's see if we can't fix that. There we go. Okay. And so let's go ahead and draw our desired curve first at point B. And so remember, both of these are going to have the same percent overshoot, but they're going to have a different settling time. So for instance, at point B, maybe we have something that looks like this. And so again, it's going to oscillate about our final value, but for point B is going to settle sooner. And so of course these oscillations should have some regular frequency. Any deviation from that is just my inability to draw that accurately. So now for our pole at point A, we have the same percent overshoot, so we should be going up to the same peak value. However, we have a longer settling time. So what that's going to look like is something like this maybe. So we have the same percent overshoot there, but we're taking a longer time for those oscillations to die down. And so just roughly looking at this, we could say maybe our TS2 is going to be somewhere here, whereas our TS1 is maybe somewhere here. And so again, that's just what this is going to look like graphically. And of course, we can think there's some physical system behind this as well. So if we go back to our basic elevator example that we like referring to, we can say, yes, the elevator, if we're going from floor 1 to floor 3, it's going to go a little above and then oscillate about floor 3. And the difference is if we have system B, that oscillation is going to end sooner, whereas for system A, it's going to spend more time sort of oscillating about that final value. Okay, so that is our problem. Let's now turn our attention to talking about generally what types of solutions we have available. So we have a couple different options. So our first option is a really sort of simple one, in theory at least, is we can just replace our system with some system that has a root locus in our desired point. So we can replace system with some new system that has a root locus. And if we're talking about the specific example above, we can say it has some root locus at that pole location B. So obviously this isn't going to be a good approach because we don't want to be redesigning, redoing, just completely overhauling, replacing a system each time we want to make some little change. So obviously not a good approach because it's of course expensive if we're doing this even just once, let alone multiple times. It's time consuming because again, remember there's some physical system behind this root locus and it's not a good long-term solution either. So not good long-term, because maybe we come back, later and we say, well, instead of at point B, we really want to have some different settling time, or maybe we want to have some particular peak time. And so maybe we want to adjust to this point here, and we can call that C. And so that could have some peak time TP1. And so we don't want to have to be replacing or redesigning this system each time. So because of all those reasons there, we don't want to be doing that. So what we're going to do instead is we're going to augment or compensate the system. And so that's what we're going to spend the rest of this unit talking about, is different ways that we can do that. So we're going to augment or compensate the system. And so ultimately what that's going to look like is we're going to be adding different poles and zeros. And as we would expect, if we have additional poles and zeros, that's going to change our root locus. So our compensated, so this is going to give us what we call a compensated system. And again, the key thing here is that we are adding additional poles and zeros, and it's going to result in what we call our compensated system. And so what we're going to see in the block diagram in the next video is typically this is done on the low power side, or before we get to what we called in our introduction videos, the plant. So this is on the low power end of our system. And again, we'll see details on that in the next video here. So then specifying that a little bit further, when we're augmenting or compensating this system, we have two general areas that we're looking to adjust or improve. So two general areas to adjust or improve on. And so depending on which one we're trying to do, we're going to have different approaches. And so we're going to look at sort of each of these in turn, and within each one of these we're going to talk about different approaches. So the first one is sort of as we saw in our rough example above, is our transient response. And so with our transient response, we're going to see that improvements can be realized by adding differentiation. So improvement realized by adding differentiation. And we're going to talk about a little bit, of course, how do we actually do that. We're not going to get into all the details of physically what's going on, but I'm going to at least refer to this in the textbook, just because we do have limited time, unfortunately. But this is one of the main things, again, that we want to adjust. Maybe we want to make that settling time shorter, or the peak time shorter, or for some reason maybe we want it a little longer. So transient response is definitely a key thing. The second important thing, though, is our steady state error. So steady state error. And so what we're going to see here is that our improvement for steady state error is realized by adding an integrator. So realized by adding an integrator. So steady state error gives us that. And so what we're going to see is that we can adjust these two things independently. We can have this integration part, this differentiation part. With each of those, we're also going to have some proportional part. And so the proportional part is talking about our gain that we've considered previously. And the last thing we're going to look at the end of the unit is sort of putting all of these things together. So we have that proportional part. We're also going to have this integration part for our steady state error. And then we have this differentiation part to adjust our transient response. So sort of the end goal here, if we're wanting to adjust all of these things, is something called a proportional plus integral plus differential controller, or a PID controller for short. And we're also going to look at some alternatives to these, this PID controller, but it's the same basic idea, just a little different approach.